Okay, so today we're going to talk about the concept of implicit differentiation. Now what this is we're taking derivative of a function with respect to x, but there's a variable that does not have an x. We will need to include a d blank dx next to each derivative. For example, if I want to take the derivative of y cubed with respect to x, I still do the derivative of y cubed. The exponent goes in front, 3, exponent decreased by 1, so it's 3y squared, but I also now need to include a dy dx into this problem. If that would have been z to the fourth, it would become 4z cubed dz dx. So you always need to be careful when you're doing derivatives of other variables. You must include a d blank dx, or with respect to y, a d blank dy, or respect to t, a d blank dt. Whatever the variable is you're taking derivative with respect to. Now, in addition to that, for the most part, your derivatives are always just simply very straightforward. It's f prime of x equals blank. That's because it was only a function of x. Now, because there's more variables, we need to actually solve for the dy dx, or the dz dx, or whatever it happens to be. So, for example, I want to find dy dx by implicit differentiation. So, derivative of x squared becomes 2x. Derivative of y squared is 2y dy dx. Derivative of 9 is 0. I don't need to include a dx because it's the variable I'm taking derivative of. I don't need to have a dx part for that. But if it's a different variable like y, that's why I must have a dy dx here. So if I want to solve for dy dx, I must subtract 2x over. So I have 2y dy dx equals a negative 2x. And then to solve for dy dx, I must divide both sides by 2y. The 2's will cancel, leaving just negative x over y. And that's the value of dy dx. That's how I'm solving by implicit differentiation. I take the derivative of each individual pieces, apply all the same rules, the power rules, product rules, quotient rules, whatever it happens to be, chain rules maybe, and anywhere there was a y, it must have a dy dx after I do that derivative. So for example, this one. So the derivative of x cubed is 3x squared. Now, negative xy is a product rule. The first expression is negative x, second expression is positive y. So the derivative of negative x is negative 1, so it's just negative 1y. And then plus our first times the derivative of the second, which is just simply dy dx, because derivative of y is 1. And then plus derivative of y squared is 2y dy dx. And that equals 0 because derivative of a constant is 0. So the goal was to solve for dy dx. Every term that's not a dy dx moves to the right-hand side. Every other term stays where it is. So I have negative x dy dx plus 2y dy dx equals, I'll move the negative y to make it positive, move the positive 3x squared and it becomes negative. Now, I have to get rid of negative x and 2y, so what I want to do is I want to factor out the dy dx, because that's what they have in common, leaving negative x plus 2y. Because now that I've factored out the dy dx, I have this as a single term, I can just divide both sides by this expression, negative x plus 2y, and I'll have solved for dy dx. So dy dx equals y minus 3x squared all over negative x plus 2y. That's what we're doing. And you have to be very careful with each one of these derivatives. Product rules will still come into play. You need to be very careful with those product rules. Derivative of the first times the second plus the first times derivative of the second. And any time you take the derivative of y, you must include a dy dx into that problem. So why don't you go ahead and try this one on your own, using what we've just talked about. Use your product rule carefully here because you have x cubed times y cubed. And again, anytime you take the derivative of y, you must include a dy dx. Once you've done your derivatives, move everything that does not have dy dx to the right-hand side. Everything it does, stay on the left-hand side. Factor it out, to then divide by whatever is left over. So go ahead and pause the video while you work on that. Once you are done, unpause it and see my solutions and my explanation for that particular solution. Okay, here's how the derivative is going to work. Again, derivative is product rule, so derivative of x cubed is 3x squared times the second function y cubed. Plus our first function x cubed times the derivative of the second And derivative of y cubed is 3y squared dy dx. Derivative of y is just simply dy dx. Derivative of x is just simply 1. So I'm going to move all the dy dx's over to the same side and combine them. So I'm going to factor out the dy dx, leaving just 3x cubed y squared minus 1. Because it's really 1 times dy dx here. And I move the 3x squared y cubed to the right-hand side to get 1 minus 3x squared y cubed. And then divide by the factored expression to get dy dx equals 1 minus 3x squared y cubed over 3x cubed y squared minus 1. Okay, this one's a little more complex. It's going to be a little bit longer, but the same concept is going to hold true. I want you to do this on your own. So you're going to pause the video, work it out, and see if you get my same solution. When you're done, or if you're lost, unpause it to then see what I've done for this problem. Again, step by step, be careful with your product rules in these spots, and you'll be okay. Alright, so again, this one's a little bit longer, but as long as you're careful, you will fine. The derivative of x cubed is 3x squared. Then again, our product rules, the derivative of the first, negative 3x squared, becomes negative 6x times the second, y, minus our first expression, 3x squared, times derivative of the second, derivative of y is just simply dy dx. And the next one, derivative of 2x is 2, so it's 2y squared. Derivative of y squared is 2y dy dx, that's why it's 2x times 2y dy dx. And derivative of 12 is 0. So the dy dx I leave on the left-hand side and factor it out, leaving negative 3x squared plus 4xy with our dy dx. And to move everything else over, that's why it's a positive 6xy, negative 3x squared, and a negative 2y squared. We then divide by the factored expression to get 6xy minus 3x squared minus 2y squared, all divided by negative 3x squared plus 4xy. So this implicit differentiation will work no matter what type of function we're dealing with. So even if I have trig functions, I still apply the dy dx process. Anywhere I take the derivative with respect to y must have a dy dx. So here is a product rule. Our first expression is 3 sine x. Our second expression is cosine of y. So derivative of 3 sine x is going to be 3 cosine of x times our second expression, cosine of y, plus our first expression, 3 sine of x, times the second, well, derivative of cosine is negative sine, and derivative of y is dy dx. Derivative of 5 is 0. So from here we want to solve for dy dx. So what I'm going to do is I'm going to move the 3 cosine x, cosine y to the one side. I have negative 3 sine x, sine y, dy dx equals negative 3 cosine of x, cosine of y. So the negative 3's will cancel out. And when I divide by sine of x, sine of y, we'll get dy dx equals cosine of x, cosine of y over sine of x, sine of y. Well, cosine over sine is cotangent. So really, dy dx equals cotangent of x, cotangent of y. Just simply a simpler way of writing that particular expression. Again, all we did was plot our product rule to get our 3 cosine of x, cosine of y, then 3 sine of x times negative sine of y, and then our dy dx because we took a derivative of a function with a y. And then from there, it's the same process. Move everything that's not dy dx to the right-hand side, and then divide out whatever's with their dy dx. Now, this one's going to be a little more complex, so I'm going to work this one for you. Again, it's going to require us to use our chain rule in addition to our implicit differentiation. So notice we have the expression q, so its derivative, I rewrite the 3 in front, our inside is sine of 2x minus cosine of 2y, decrease the exponent by 1. And then times, well, the derivative of the inside, derivative of sine of 2x is 2 cosine of 2x. Derivative of cosine of 2y is a negative sign, but the negatives will cancel, that's why it's going to be plus 2 sine of 2y. And then we have our dy dx. And then derivative of 6 is 0. Now this may seem a little nastier than you might want to deal with, but it's actually pretty easy. If I want to solve for dy dx, I must get everything over to the right-hand side. Well, since I have a product, I should divide both sides by 3 sine of 2x minus cosine of 2y squared, well, 0 divided by any number is 0. So this goes away. This is irrelevant. All that's left is 2 cosine of 2x plus 2 sine of 2y dy dx. Now I can subtract over the 2 cosine of 2x to get 2 sine 2y dy dx equal to 2 cosine of 2x, negative 2, sorry. The 2's will cancel. And when I divide by sine, I'll get dy dx equals negative cosine of 2x over sine of 2y. Unlike the previous problem, this does not become cotangent because our angles are both different. Notice if I go back, the angles are both x's for cosine of x over sine of x. Our angles are both y's for cosine of y over sine of y. That's why I could rewrite them as cotangent x, cotangent y. Here, I've got cosine of 2x, sine of 2y. Yeah, they both go to 2, but they have different variables, so they can't combine. And that's as far as that problem goes. So again, we applied our chain rule. That's how we got the 3, and then the inside sine of 2x minus cosine of 2y squared. And then the derivative of the inside was our 2 cosine 2x plus 2 sine of 2y. And again, took a derivative with respect to y. That's why dy dx appeared. Now if I want to solve for dy dx, this portion is irrelevant because it has no dy dx. It's a product. So if I divide by it, 0 divided by anything is still just 0. That's how we just left with this portion right here, and then we solved it that way. Okay? Alright, now, one interesting application of using implicit differentiation is we can go back and talk about what is the value of the derivative at a single point. Because again, dy dx represents the derivative with respect to y. So what we're going to do is we're going to do the same thing. We're going to take the derivative of x, y equals 6, solve for dy dx, but then we're going to plug in the given values of negative 6 for x, negative 1 for y to figure out what is the value of this derivative dy dx. So, again, product rule. Derivative of the first is 1, so it just becomes y, plus the first times derivative of the second, so it's x plus dy dx equals 0. Derivative of 6 is 0. So, to solve for dy dx, we must subtract y from both sides. So we get x dy dx equals negative y. Then we divide both sides by x to get dy dx equals negative y over x. I now plug in the given values, so negative of negative 1 divided by negative 6 will give us negative 1/6 for our answer. Now this should look very similar to something we've done in the past. If you remember, plugging into the points, the derivative was the value of the slope of the tangent line to a function. That's what this is right here. This right here represents the slope of the tangent line to the function x, y equals 6 at the point negative 6, negative 1. So we can still apply those different rules there to find these different answers. So same thing here. We're going to take the derivative of both sides, and we're then going to solve for dy dx, and then plug in the 2 for x and 3 for y. So what I want you to do is, since this is similar to what we've just been doing, you should be comfortable with implicit differentiation at this point. I want you to go ahead and take the derivative on your own, solve for dy dx, and plug in for x and y. So you go ahead and pause this video, and then once you're done, or again, if you're stuck, unpause it and see what I did. Good luck. Okay, so your final answer should be a positive 2/5. And how we got that? Well, again, derivatives. Derivative of x cubed is 3x squared. Derivative of y cubed is 3y squared dy dx. And then equals, we have our product rule, 6x and y. Derivative of 6x is 6, so that's why it's just 6 times y. Derivative of y is dy dx, that's why it's 6x times dy dx. And then the derivative of negative 1 is 0, that's why there's nothing else here. So, to solve for dy dx, we need to move all the dy dx's to the left side, and everything else to the right-hand side. That's why it's 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. I factor out the dy dx to get 3y squared minus 6x. We then divide by it to get the expression 6y minus 3x squared over 3y squared minus 6x. You then plug in 2 for x, 3 for y. You work it out and get your answer. It should be a positive 2/5. So at this point right here, just doing the exact same process of solving for dy dx, we now just plug in a coordinate point for x and y into our final answer. Now, implicit differentiation also can go further. I can do derivatives of multiple, first derivative, second derivative, third derivative, and so on. I can do the same thing for implicit differentiation. Finding d squared y dx squared is finding the second derivative for implicit differentiation. Now, this is a little bit more complex than just usual second derivative, so bear with me. First part is, as always, you need to solve for dy dx. So, we have x squared plus y squared equals 20. So, when I take the derivative of x squared, I get 2x. Derivative of y squared, I get 2y dy dx. Derivative of 20 is 0. I now need to solve for dy dx, so I move the 2x over. Get 2y dy dx equals negative 2x. I'm going to divide both sides by 2y. I get dy dx equals a negative x over positive y. That's important. We need to work with this now. Now, finding the second derivative, well, now that I have dy dx all by itself, I take the derivative of the quotient. So this becomes a quotient row problem. The derivative of the top is negative 1 times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. So we have the second derivative, d squared y dx squared, is equal to negative y plus x dy dx all over y squared. We're not even close to being done at this point. We've now taken the derivative, we evaluate, but now we need to work with it. What is dy dx? Well, dy dx is negative x over y. So I can rewrite this as negative y plus x times negative x over y, all divided by y squared. So when I multiply in there, I get negative y minus x squared over y, all over y squared. So all I've done at this point is I've taken my derivative dy dx to get the d squared y dx squared, and then I plugged in dy dx in for what I know dy dx equals, negative x over y. I now have a complex fraction, where I have a fraction inside a fraction. I can't leave it like this, so multiply top and bottom by that complex part of the fraction, the y, and I get the second derivative to be a negative y squared minus x squared over y cubed. And again, I'm not quite done yet. Because if you take a look at this, the reason why I know I'm not quite done is, for the most part, from a lot of these problems, the end result up top is somehow related to the original expression. Not always, but sometimes. So if we look at this, I have x squared plus y squared. Well, don't I have an x squared and a y squared in this expression? The only difference is they're both negatives. So let's take a negative out, and then rewrite it in a different order. If I take the negative out, they're both positives, and put them in the proper order, I have x squared plus y squared. Well, isn't x squared plus y squared equal to 20? So that really means it's negative 20 over y cubed. That is the value of the second derivative, d squared y dx squared. Pretty interesting. That's how we want to go about doing these processes. You want to solve for dy dx first for these problems, and then once you have that, you need to take your second derivative, evaluate that properly, and you'll find a dy dx term showing up again, most likely. When it does, you plug in what you know dy dx equals, and then continue your algebra manipulation from there. Now, not all problems will require you to plug back in. They're not always going to do that. Sometimes they don't. Either way, though, your numerator should always factor as far as possible to see if you can get anything to look like the original expression. So then you can plug in and make it even simpler. Okay? So that's the concept of finding the second derivative, d squared y dx squared. There can be more complex ones than that. It's pretty much the same concept. It's just simply a longer process, a more complicated process of solving it. So that's where we're going to stop right here. We got one last thing to talk about for our basic derivatives. This is the concept of related rates, which is going to involve everyone's favorite thing, word problems. So I will see you next time.